Happy Pi Day, everybody! I am sad that I'm not going to be there to celebrate this holiday with you guys, but I wanted to still create a little video to explain all of the great things that I would normally cover involving Coulomb's law. So anyway, this is just my little way, my little picture and image to get you inspired to be aware of Pi Day and go out, have a piece of pie, go to Baker Square, all that fun jazz, celebrate, have fun, be geeky. Yay! To begin with, I want to make sure that you've submitted your electric charge problems. That worksheet was from the last time we had class, and I'd like you to submit that using the submission form, please. And as bell work, if you want to pause this, and this is just kind of a general kind of piece, pause the video. Take time to answer the questions. Work through it on your own. Use your calculator. Some of these problems are hard and a little tricky and easy to get caught up on. So use this as an opportunity to really stop, slow down, make sure you know what you're doing. And like I said, pause it whenever necessary. Take notes. Make sure you understand this stuff thoroughly. So first of all, as the bell work, what is the charge on a single electron? And what's the charge on a single proton? Take a few moments, go back to your notes if you need to. Make sure you know what you're talking about on that front and that you're comfortable with that, because this is a number that we're going to be using a lot as we go along. And hopefully you wrote this down. First of all, if we talk about charge, we use the variable Q to represent charge. QE is how we typically represent it. And the charge on a single electron is negative 1.6 times 10 to the negative 19 coulombs. So remember, the C represents coulombs. And we use just the letter C to represent those units too. And the charge on a single proton is actually the exact same value, just positive. So 1.6 times 10 to the negative 19 coulombs. All right, so now with this in mind, we're going to start to look at a little kind of kickoff kind of demonstration. The idea is, and as you see up front, the idea is that you have two balloons hanging down. We want to use that to help us understand what happens when we have objects that are charged. So watch and enjoy the following video. Okay, so right now we have two balloons hanging down. They're hanging straight down, they're not charged, they're neutrally grounded, there's no charge on them, and as a result, they'll be hanging down. Once they settle down, they'll be hanging straight down. If I take both balloons and I charge it up, so now both balloons are now negatively charged. Wait for it. There we go. You can see that now both balloons are pushed away. They're both negatively charged, so they're repelling each other. And that's what we're going to analyze. Okay. So now let's look at why that happened. Now we know that on our balloons, when they're originally hanging down, we know we have a neutral balloon. So neutral balloons mean that we have the same number of electrons as protons. But now when I rub my hair against it, it actually creates a negatively charged balloon. The balloon steals the electrons from my hair, and now it has more electrons than protons on it. And if we have a negatively charged object, and both of them are negative, we know that like charges are going to cause this repulsive kind of response, a repulsive force. So what we want to talk about is that force that we have acting on our object. So the idea is, if it's a repulsive force, we know that we're going to have these force values and force arrows pushing away from each other. So two forces that repel. And that's because they are like charges. Now I want to analyze specifically those two different forces, this force and that force. They're pushing each other away, and I want to talk about where that force and why that force is happening. So first of all, let's label this balloon on the left A and the other one B. So I know that when it comes to the forces, the force on the left, the balloon on the left, this one, that force is coming from the charge of B. So this is actually the force of B acting on A. Likewise, the force on the right is actually the force of A on B. Those forces are what we call the electrostatic force. Just because a balloon is in the presence of another charged object, so a charged object in the presence of another charged object, it creates this electrostatic force. It's the same force that caused our little pith ball that you painted and the charge rod to repel each other. Two charged objects acting together in the same field cause this repulsive force. It's an invisible force. It's called a field force, just like gravity. When gravity causes two objects to be pulled towards each other. And we can kind of draw that example. We have Earth, let's call this Earth. We have our object, some small little object, some small little middle of mass. Let's call it like a balloon, or if it's a medicine ball. And that causes then the force of gravity. And the force of gravity actually acts in both directions. It causes the mass to fall down towards the Earth, and the same force is actually acting on the Earth from the small mass. Now, this idea is actually coming from Newton's third law, the idea that forces come in pairs, even with field forces. So when we talk about this force and that force, those two forces, the force of B on A, is actually equal to the force of A on B. We now want to figure out how we can find and solve for those two forces, and that's going to be one of our goals today. So to start, if I know I have like charges repel. So that means you create this repulsive force, or forces that are acting in opposite directions away from the other charge. At the same time, we also have charges that are opposite. Opposite charges create an attractive force. So as a result of that, these two forces will be coming together and pulling the objects towards each other. Now, once again, this force is equal to that force. This force is equal to that force. And they're both caused because of the fact that these are two charged objects acting near each other and in the same field. So now I want you to pause. Pause this and think about what causes the electrostatic force to change. So pause it, brainstorm, maybe share it with a partner. What things could cause that electrostatic force to change, get bigger? So think about it in terms of the balloon. What would cause the force acting on the balloon to change and get larger? Now, I hope that when you brainstormed, you came up with the idea of the charge. If you add more electrons to the balloon, or a different charge to the balloon, that would cause the force to change. Also, distance, how far apart those balloons are. Imagine me taking the two balloons up at the front of the room and separating them several meters apart or across the room. Those charges no longer are going to be near each other, and therefore they're not going to be causing that same force that's going to be, that's going to be present. It's going to be a smaller force. So charges, distance, those are the things that are going to affect our object's force, and that specifically is the electrostatic force. So let's start now by looking at two different charges, two negatively charged objects. We know because they're negatively charged, it's going to create a repulsive force. And I want to ultimately figure out how big is that electrostatic force. And that's going to be what our goal is today. Now, what we can see is that the object A has 1 million more electrons than protons. So if I have 1 million more electrons than protons, and I'm looking at that, I know that my n value for object A is going to be 1 million. 1 million more than the other. So think of this in terms of our equation that we've been working with. So if I want to find the charge then, capital Q, the charge on object A, I'm going to want to use the equation Q equals n times little q. Now little q is going to be the charge on a single electron, so negative 1.6 times 10 to the negative 19 coulombs. So if I want to plug this in now to get my big Q, and I'd like you to use your calculator to do this too. Big Q equals 1 million times negative 1.6 times 10 to the negative 19 coulombs. And if you plug that into your calculator, we find that QA, or the charge on this particular object, is going to end up being negative 1.6 times 10 to the negative 13 coulombs. So once again, this is 1 million more electrons acting on that object. Now the other one, which is going to be our B, so B over here, B is actually going to be the same number of electrons, more electrons than protons. So as a result, my charge on B is actually negative 1.6 times 10 to the negative 13 coulombs also. So now let's start to relationship build. If I made my QA value bigger, my QA went up, what would happen to my electrostatic force? Just think, so more charge, more electrons would cause my force to go up. Same thing for my QB. If I cause my QB to go up, that would mean my force would go up also. Now the next one's a little bit trickier. If I had my R here, and I caused my R to get further apart, bigger R, these are moved further apart. If my R went up, it would mean that my force was going to go down. So what we have is an indirect relationship there. Indirect, while the other ones are direct. And now let's use this to come up with our equation that will represent our force. All right, so now that we have this idea of relationships, I want you to pause this video real quick and see if you can figure out what is the equation going to look like when we look at these variables. So the variables we came over here as they relate to F. So F is going to be on the left side of the equation. And I want to figure out where my other variables are going to be placed on the right. So first of all, let's start. So pause it right now to work through it. And then I'll kind of walk through my solution too. First of all, let's start with our QA. If your charge went up, your QA went up, and your force goes up, that would mean my QA goes up into the numerator. Same thing is going to be true about my QB. As my QB goes up, my force goes up. Direct relationship means it's up in the numerator. R has an indirect relationship, so that means it goes down into the denominator. Now this gets a little weird now because there are a couple pieces that are not completely clear and apparent based on the relationships we've developed. The R is actually squared. So the denominator, R value, is an inverse square relationship with force. So distance has an inverse square relationship with the force value. In addition, there's actually a constant out in front of this. We call this Coulomb's constant. Coulomb's constant is K, and that K value is actually always going to be 9 times 10 to the ninth. So that K value is always 9 times 10 to the ninth, Newton times meters squared over Coulomb squared. So wherever you see the K, you always plug in this number. Now there are a couple other pieces of this. Because forces always come in pairs, we know that could create an attractive force or a repulsive force. And in either case, we see that the forces are pointing in opposite directions. So this force equation actually doesn't tell us direction. It only tells us the size or the magnitude. So it's a magnitude only equation. And because of that, our charge value and the size, the direction, the size or the charge as being positive or negative really doesn't influence this equation. So we actually put these absolute value signs around each of our Q values, each of our charge values. And this is now our Coulomb's law equation. K, representing the 9 times 10 to the ninth, the absolute value of our charge A, the absolute value of our charge B, and then that's all going to be over R, or the distance squared. Now remember, a couple things to point out. Your R is always going to be measured in meters squared. With meters. And then that's going to create the meters squared. The Q value is always going to be coulombs. We're going to use that in coulombs for both of them. So my charges are measured in coulombs. And with that, with the K value that we have here, that's going to cause my resulting value to become a force using newtons. So meters, coulombs, and then that creates then a force value of newtons. This is only the first half of the video, so please stop this and watch the other video now, and that will help us with coming up with how to apply this equation.